So in section 6, we're going to be given 4 new sets of identities. So sum and difference identities, double angle identities, power reducing identities, and half angle identities. What we're going to be using these for, or all I'm going to ask for you, or that you guys are able to use these for, is to evaluate to find, or use them to find the exact values for angles that are not necessarily on the unit circle. So not any angle, or we can't use any angle to do this, but some angles that we can write as, the sum or difference of 2 unit circle angles, or a half of a unit circle angle, or twice a unit circle angle. Some of these we can use these identities for to evaluate. So let's just jump in and do some examples. So let's do some sum and difference examples first. Let's say we want to do sine of 15 degrees. So 15 degrees is not a unit circle angle, right? Can I write 15 as the sum or difference of 2 unit circle angles? Well, if I go back and I look at my unit circle, I see that there's actually a bunch of options where I can write it as a difference. 45 minus 30 is 15. Or 60 minus 45 is 15. Or 135 minus 120 is 15. So there's lots and lots and lots of options here. Does it matter which one I choose? No. Anything will do. So for the sake of argument, let's use 30 and 45. So we're going to say 15 is 45 minus 30. So the way we're going to think about this as sine of 15 is equal to sine of 45 minus 30. Cool so far? And now I'm going to go to my identity list and find the angle difference formula for sine from my identity list. So I'll scroll over here. Sum and difference identity. So the one that I want is sine. Now notice that the way we've written these or all these sum and difference identities has plus and minuses in here. This is really 2 identities written in one line. So we want a difference. So we're going to we need the sine of x minus y. So we're going to use the bottom of the plus or minus. Does that make sense? If we had been doing addition, we would do the top of the plus or minus. So I'm going to fill this in. So this says that sine of x times cosine of y minus sine of y times cosine of x. Is everybody okay with how I filled that into my formula? And now if I look, everything in this formula is a unit circle angle measure, right? So I'm just going to go to my unit circle and pull the values for these. So sine of 45, I go to the 45 degree and I look at the y coordinate. That's root 2 over 2. Cosine of 30 degrees. I look at the x coordinate at 30 degrees. That's root 3 over 2. Sine of 30 degrees, I look at the y coordinate at 30 degrees. That's 1/2. Cosine of 45, I look at the x coordinate at 45 degrees. That's root 2 over 2. So far, so good. I go ahead and multiply these fractions. To multiply fractions, we just multiply straight across. So root 2 times root 3 is root 6. And 2 times 2 is 4. 1 times root 2 is just root 2. And then 2 times 2 is 4. And since these have a common denominator, I could really write this as a single fraction. But remember from last year, we cannot combine different kinds of radicals through addition and subtraction, so that's as good as we can do. Does that feel okay? Nothing too tricky about that, right? You're just basically plugging stuff into the formula and then evaluating with the unit circle, which are all things that we've done before. Let's do one more example with an addition or subtraction one, and then we'll move on and do some other examples. So let's say we want to do cosine of 5 pi over 12. Now this is a little trickier to figure out the two angles that you need because it's a fraction, right? We've written this angle measured in radians as opposed to degrees. You guys notice that right away? Here's the trick. If I go look at my unit circle, all of my unit circle angles have denominators of 6, 4, 3, or 2. Everybody agree with that? So what I'm going to do is I'm going to try to break up that fraction of 5 over 12 into the sum or difference of two fractions that will reduce. Both fractions need to reduce. And then the only ways that 12 is going to reduce is going to give me a denominator of 2, 3, 4, or 6. Like I can't get it to reduce another way. So I'm going to be good at that point. Is everybody okay with that idea? So I'm going to look at 5 pi over 12. And I want to rewrite 5 pi over 12 as the sum or difference of two fractions. It doesn't matter. I think in this case a sum would be easy because I noticed that 5 is the same as 2 plus 3. Everybody okay with that? So I'm going to write this as 2 pi over 12 plus 3 pi over 12. And I like that because both of those fractions reduce. You guys agree with that? Now, is there another addition problem that we could have written this as to make it reduce? No, but that's okay. Could we have done a subtraction problem? Sure, you could have done like 8 pi over 12 minus 3 pi over 12. That would have been okay. Both 8 over 12 and 3 over 12 reduced, so that would have worked. You know, so just kind of like, you need to make sure the fraction reduces. It's basically all you need to do when you break it up into the two chunks. Is that okay? So now that we've done that, we can say, okay, cosine of 5 pi over 12 is just cosine of pi over 6 plus pi over 4. I go and I look at my identity sheet at my angle sum formula for cosine. So here we're doing additions. So we're going to take the top symbol. So in that case, cosine of x plus y is going to be cosine x cosine y minus sine x sine y. Is everybody okay with how I'm reading the identity sheet there? So these symbols here are going to tell you whether you want to use the top symbol or the bottom symbol on the right half of it. Oops. Okay. So now I'm going to go ahead and fill in my formula. So that's going to be cosine of pi over 6 times cosine of pi over 4 minus sine of pi over 6 times sine of pi over 4. I will go to my unit circle. Cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Sine of pi over 6 is 1/2. And sine of pi over 4 is root 2 over 2. Then I just multiply my fraction straight across. Root 3 times root 2 is root 6. 2 times 2 is 4. 1 times root 2 is root 2. 2 times 2 is 4. And then we have a common denominator, so I can just write these as a single fraction. And I'm done with that. Note that that's the same answer as the previous problem. If I were to convert 5 pi over 12 into degrees, you'd see that's going to be 75 degrees. So the fact that sine of 15 and cosine of 75 are the same value shouldn't be surprising, because 15 and 75 are complementary. It's basically the cofunction identity from last chapter going on there that we had talked about before. The other thing that we can do with these, or that you'll be asked to do with these, is to go the opposite way. Okay, so let's say that we're given the expression sine 47 times cosine 23 minus cosine 47 times sine 23. And we're asked to write this as a single trig expression. So what I need to do is I need to look at this as like sine x times cosine y minus cosine x times sine y. And go look at my identity sheet and see if this is the angle sum or difference formula for sine, cosine, tangent, etc. So we'll just scroll on over. So I see I have sine x times cosine y, and then cosine x sine y. So that's what I have, right? And we had a minus sign in the problem. So that means that's an angle difference for sine. So what this really is saying, or what we can say here then, is this is sine of 47 minus 23. or sine 24. And we're done. Going backwards is easy. Does that feel okay there? Or we're just using the formula? Let's say we want to use the power reducing. Identities to evaluate. Let's say we have sine squared of 3 pi over 8. So I'm going to go look at the power reducing identity since the instruction is telling me to use one of those. So the power reducing identity I'm going to need to use is going to be this one. Okay with that? So in our case, we don't have to worry about messing around with that angle inside of my sine squared at all. It's just part of the formula. So in our case, our x is 3 pi over 8. So I'm just going to be plugging 3 pi over 8 into the x on the other side of my formula. Everybody good? Okay. So this is going to be 1 minus cosine of 2, and then times x, which is 3 pi over 8, all over 2. So far, so good. Next thing I'm going to want to do is multiply here. I'm going to do this multiplication by thinking about 2 as 2 over 1. And then I'm just going to kind of reduce as I multiply. So that's really going to turn into cosine of 3 pi over 4. Which is great because I recognize 3 pi over 4 as a unit circle angle. So I can go look up the value for cosine of 3 pi over 4 on my unit circle. That's root 2 over 2. So far, so good. The last thing I want to do is try to simplify this because I don't like the fact that I have a fraction inside of a bigger fraction. Everybody kind of see that? So here's the way that we're going to do that, is I'm just going to multiply the top and bottom of this fraction by 2. So when I multiply the 2 to the 1, I just get 2. When I multiply the 2 to the root 2 over 2, the 2 in the denominator cancels with the 2 that I'm multiplying in and leaves me with just the square root. And then I multiply the 2 to the denominator and I end up with 4. That's it. So what have we been doing so far? Really just kind of plugging stuff into formulas, right? And then going to the unit circle and pulling some values and doing a little bit of like arithmetic. Does it get harder than this? Not really. Not what I'm going to ask you guys to do. I mean, could it? Sure, but this is why we've allotted only the one day to do this. So this is probably as tricky as I could make one of these things. So here we have cotangent squared of negative 165 degrees. So let's go look at our power reducing formulas. And if I look there, I see, uh-oh, I have no cotangent squared formula under my power reducing. What am I going to do? Is sine, cosine, or tangent related to cotangent? Yeah. Which one is most directly related to cotangent? Tangent. And what's the relationship between tangent and cotangent? They are reciprocals. So what is the double or the power reducing formula for cotangent squared going to be? Yeah, it's going to just be the reciprocal of tangent squared. So it'd just be like 1 plus cosine 2x over 1 minus cosine 2x. No big deal, right? Just make the reciprocal. Everybody okay there? All right. So let's go ahead and fill in then. So we have 1 plus cosine of 2 times our x is negative 165. And then 1 minus cosine of 2 times our x, which again was negative 165. 2 times negative 165 is negative 330. I'm just going to write the negative 330 like right there. Is that okay with everybody? Just to save having to recopy everything again. Now, is negative 330 a unit circle angle? No, because it's negative, right? So what should we do? I'm just going to find an angle that is coterminal to negative 330 that is on my unit circle. So what do I have to add to negative 330 to find something coterminal to it? 360 degrees. Everybody's okay with that? And I know I'm adding because the angles on my unit circle are all positive, right? So if I add 360 to negative 330, I just get 30 degrees. Everybody so far so good? I go to my unit circle now and pull my values. So cosine of 30 degrees is root 3 over 2. Everybody so far so good? Now we're going to get rid of the fractions inside of fractions. What should I multiply to the top and bottom of this? 2. So when I multiply 2 times 1, I get 2. When I multiply 2 times root 3 over 2, the 2's cancel, and I'm left with just the root 3. 2 times 1 is 2. And I multiply 2 times root 3 over 2. The 2's cancels, and I'm left with just root 3. So far, so good? Is this our best answer? What's wrong with it? Do we like radicals in the denominator? Oh, Mr. Kulik, really? Now, getting rid of the radical in the denominator in this particular problem is going to be a little bit tricky because the radical is being added or subtracted to something. So instead of just multiplying the top and bottom by root 3, that's not going to do it. We have to multiply the top and bottom of this fraction by the conjugate of 2 minus root 3. If you remember, the conjugate means just the same thing with with the opposite sign in the middle. So we're going to multiply the top and bottom by 2 plus root 3. So we can really think about parentheses being around all of these things. When I multiply things together in parentheses, what do I have to do? Starts with an F. FOIL. So when I multiply the numerator, I do 2 times 2. 2 times root 3. Root 3 times 2. And then root 3 times root 3, which is just root 3 squared, but I'm just going to write 3. I'm just going to skip that step. Cool? Do the same thing in the denominator. So I have 4 minus, plus 2 root 3 minus 2 root 3 minus 3. Notice here the plus root 3 and the minus root 3 cancel out. So there's no more radicals in our denominator. That's excellent. 4 minus 3 is just 1, so I'm left with 1 in the denominator. In the numerator, 4 plus 3 is 7, and then 2 root 3 plus another 2 root 3. We just add the coefficients and keep the radical part the same. So really, we could just write this as 7 plus 4 root 3. How's that feel? Okay so far? Okay. And the next set of identities we'll talk about are the half angles. So let's say we have cosine of 22.5 degrees. If I go and I look at the half angle identities, I'm going to need to rewrite, I used cosine, right? In my example there, is that right? I wrote cosine of 20, okay. I'm going to have to rewrite 22.5 as something divided by 2, where that something should be a unit circle angle if I'm able to do this. So what divided by 2 gives me 22.5? I'm just going to multiply 22.5 by 2, which is 45. Everybody's okay with that? So this is going to be cosine of 45 over 2. Now, when I look at the half angle identity for cosine, it gives me a plus or minus. We're going to figure out right now whether this should be plus or minus. We're doing the cosine of 22.5, right? What quadrant is 22.5 in? Quadrant 1, 2, 3, 4. That's in Q1. Everybody cool with that? Yes?
You know that because you got 45.
I mean, it's just like if I was going to draw a 22-degree angle, it's there, right? We're just talking about drawing a standard position. Is that cool? Okay. And in quadrant 1, what do we know about the sign of cosine? Is it positive or negative in quadrant 1? Well, all silly turtles crawl. Everything is positive in quadrant 1. So we know that this is going to be the plus, not the minus. Everybody's okay with that? So we just use the angle, the original angle, to figure out whether the thing should be positive or negative, because depending on the quadrant you're in. Is that cool? So nothing tricky there. You just have to remember to do it. Okay. So now we're going to go ahead and look up cosine of 45 from the unit circle, which is root 2 over 2. Everybody's cool there? Notice that I dropped the plus or minus and just left it as positive, the whole thing, right? Because we decided it was a positive. The only issue I have here is the fraction inside of the fraction, right? What are we going to multiply the top and bottom of this by to get rid of that? 2 is close. It actually has to be square root of 2 over 2, because you can't multiply something inside of a square root unless it's also under a square root, right? Okay, so when I do that, I end up with 2 plus root 2 over 4, and that's still all under the big square root. Notice I can do a little bit of simplifying here, because if I have a square root over a fraction, that's the same thing as the square root of the top and the square root of the bottom. And the square root of 4 is just 2, right? And that's as good as we can do. What do you think? Not so bad, right? Let's go look at the homework problems. So if you were interested in doing the homework for this section as practice, I would say these ones would be reasonable to do. These ones you should be able to do. These ones you should be able to do. That's it. If you're worrying about homework problems, that would be all I would worry about. If you wanted some practices. But this is all I'm going to ask you to do on the exam. Right? If we look at the exam review and we scroll down to look at chapter 6, right? It looks almost exactly like these kinds of problems we were just working on, right? So it's not going to be anything more than what we just did here. You just have to be able to use the identities to get the exact value. So it's like being able to pick out the right identity, look the stuff up off the unit circle, and do a little bit of simplifying. But it's not too bad. Cool? Well, let's stop here. That's as much as I really need to do today.